In the last video, we mentioned that the gravitational field is an example of a vector field, and so I thought in this video it would be a good idea to derive a formula for that gravitational field. So let's start by writing down Newton's law of gravity. So Newton's law of gravity, I've already got it written here, but Newton's law says the following, that the gravitational force, so the magnitude of a gravitational force of one object exerted on the other, so this is a law about the magnitude of gravity. This magnitude is equal to some constant over the length squared of the distance squared of the distance between the centers of masses of these two objects. This is called the inverse square law, and it turns out that the constant of proportionality on the top in the numerator is the product of the masses of the objects times some universal gravitational constant g. Okay, so in this situation, this is the formula that we're going to use, but I'll write down what these constants are. So g, this is the gravitational constant, and you can look up the value of this constant. We're not going to care. We're just going to call this capital G, and keep in mind that it's a constant. And the two m's, these are constants. They are the masses of our objects. So this is a constant mass of, let's call it object 1, O1. And capital M is the constant mass of object 2. So these three numbers are not changing depending on if we have the same two objects. They're not changing. So the gravitational force is totally determined, other than this constant, it's totally determined by R, and R is the distance between the centers of mass of these objects. Alright, so I'll write this out, between the centers of mass, and then let's draw a little picture. So the idea is that if we have two objects, nice round objects here, who have centers of mass O1 and O2, and whose masses are m and m, then the gravitational force between them is proportional to this distance right here, the square of this distance. So this is the distance r, and if we choose our perspective to be, let's say that we are at object O1, so the one on the left, then we know that gravitational force is also attractive, and so the gravitational force is going to be pointing back toward us. So it's going to be pulling the second object toward us at object 1. And so this is the mix, and again, somewhere floating around here there's this constant g, which helps us compute the actual value of the gravity, the gravitational force. But Newton's law tells us that that g is constant, and that this is the formula for the length. So the magnitude of the force is always equal to this. Okay, so what we want to do is write a formula for this in x, y, z coordinates, so for three-dimensional objects. So let's set the problem up a little bit here. We've done most of the setup, but let's say that we are at an object, say object 1 is centered at the origin here. So the center of mass of object 1 is at the origin, and again the mass of object 1 is little m, and the other object, say object 2, has the center of its mass has coordinates x, y, and z. And because we only care about the center of mass for this law, we can just plot these as single points. Alright, and we'll call the mass of this one capital M. And of course, if we regard ourselves as being at the object at the origin, then the gravitational force is going to be pointing back. It's going to be attractive, right? It's going to be pointing back toward the point at the origin. By the way, the gravitational force does not necessarily need to be the exact length of this, right? The gravitational force might just be of this vector right here. But the point of this is that it's pointing back toward the origin. Okay, it's pointing back toward the origin, and in reality the magnitude of this force, gravitational force, is going to increase. So this vector is going to get bigger and longer as this point O2 gets closer to point O1. Okay, but the length of this is important because this is the r that shows up in our formula. Alright, so I hope remember that if we have a vector field, f, it can be decomposed, so any vector, just forget about the fact that this is a function, but any vector can be decomposed into a unit vector that determines its direction times the magnitude of the vector field. And Newton's law tells us the magnitude, okay, the magnitude at any point. What we need to do is find a unit vector that points in the direction that our vector field should be pointing in at every point. And just based on the picture, this is really the reason for putting everything in this scenario at the origin with the vector pointing back toward us. Just by looking at this picture, we can see that the unit vector is going to have to be the vector which points in the direction, so the opposite direction of the coordinate vector, and then becomes a unit vector, right? And so this vector u, just based on what we're working on here, this distance from the point to the origin, that's r, so that's going to be the magnitude of the vector, and then it's going to be the negative of the position vector. So what am I saying here? Well, the vector that just picks out the point, O2, points this way. This is in the right direction in some sense, but it's going the opposite direction really, right? It's in the right line, the right ray, but it's pointing the wrong direction. And so what we end up with is that this vector u should equal to the opposite direction, so negative the position vector, x, y, z, and then it has to be scaled to become a unit vector, right? But this vector has length r, and so we have to divide the whole thing by r. Okay, so there's our unit vector, and what we end up with then is for our gravitational field, this gravitational force at any point x, y, z with mass m is acted on upon this point O1, us at the origin, with mass little m, in the following way. So the magnitude of this force, according to Newton's law, is mg over r, and the direction of the force is given by this vector u, and so that gives us another the gravitational law says that's an r squared. Don't get sloppy here, Justin. So then the unit vector has a minus and then another r factor on the bottom times this position vector x, y, z. Okay, and if we just combine this whole constant here, we end up with a formula for the gravitational force at any point in space, which is now given by minus the product of the masses times the gravitational constant divided by the radius cubed, okay, divided by the radius cubed, times that position vector, x, y, z. And the minus again makes this attractive, and so there's the formula for the vector field of the gravitational force. Now, if you're going to use this, keep in mind that r is a function, and r is actually the distance function, right? R depends on x, y, and z. So the way that we've done this, we haven't actually had to work with the x, y, z coordinates for r at all, but do not forget, right, that this r depends on the point as well. All right, so there's our gravitational field.